Imagine standing in the peak of winter, wrapped in thermal insulators designed specifically for your protection. You pull out your smartphone to perform the simplest of tasks, replying to a message or capturing a moment. But for some mysterious reason, this brilliant device in your hand transforms into an inert slab of glass. You press harder, you repeat the motion, but the screen refuses to acknowledge your presence behind that glove. This is where the paradox emerges. We define these interfaces as touch screens. But the shocking technical reality is that your phone does not feel your touch at all. It remains indifferent to mechanical pressure and unconcerned with your body heat. In this moment, you are not merely a user. You are an electrical conductor attempting to penetrate an insulating barrier. To understand why the glove fails today, we must revisit the era of resistive screens, which once dominated ATMs and early mobile devices. That technology relied on pure mechanics, two flexible layers separated by a microscopic gap. When you applied pressure with any object, be it a finger, a stylus, or even a piece of plastic, the layers touched, completing the circuit. It required physical effort, and the results were low precision, a total absence of multi-touch capabilities, and a short lifespan due to repeated mechanical stress. However, the true revolution occurred when engineers decided to move away from matter and rely on fields. This saw the rise of capacitive screens. We replaced physical pressure with electrical coupling. No longer does the screen wait for you to push it. Instead, it monitors disturbances in its electromagnetic equilibrium. But this technical elitism came with a strict tax. The device became selective. It now refuses to communicate with anything that lacks very specific electrical properties, effectively removing traditional gloves from the communication equation entirely. Let us now penetrate beyond the glass into the realm where matter ceases to be a mere surface and transforms into a grid of electromagnetic coordinates. What your eyes perceive as absolute transparency is, in fact, two orthogonal layers of microscopic electrodes crafted from indium tin oxide. This chemical compound represents the pinnacle of functional engineering. It is as conductive as metal, yet as optically transparent as crystal. Imagine this grid as rows and columns that never touch, separated by an ultra-thin dielectric insulator. At every intersection, what we technically term mutual capacitance is established. Here, the controller sends electrical pulses through the rows and awaits their reception across the columns. As long as the screen is idle, the voltage at every intersection remains stable, recording a monotonous pulse that tells the device the external world is silent. However, the moment your finger approaches, the rules of physics change. You don't even need to press the glass. Your ion-rich saline body acts as a massive capacitor compared to those microscopic electrodes. As your finger nears, it intrudes upon the electrostatic field of the intersection, absorbing or stealing a fraction of the electrical charge. This electronic escape causes a sudden localized drop in voltage at that specific junction. Enter the mastermind, the touch controller. This tiny processor scans the entire grid more than 100 times per second. It does not detect touch. It detects the absence of charge. It translates this digital deficit into precise coordinates via the fundamental capacitance equation. What you perceive as a fluid glide across the screen is actually a complex mathematical processing of thousands of electrical disturbances caused by your physical presence within the device's electromagnetic field. If the screen monitors the escape of charge toward your body, why does a glove fail to facilitate this transfer? The secret lies in an elite physical concept known as the dielectric constant. The materials used in gloves, such as cotton, wool, or leather, are superior electrical insulators. This means they lack the free electrons necessary to bridge the electromagnetic pulse from the glass to your finger. From an engineering perspective, we are governed by the capacitance formula. Here, the glove plays two destructive roles. First, it increases the distance between your finger and the sensor. As distance increases, capacitance dissipates exponentially. Second is the permittivity of the insulating material. The glove absorbs and scatters the electric field before your finger can ground it. This is why the strength of your pressure is irrelevant. You are attempting to establish an electrical connection across an insulating wall. The only engineering solution that allowed the creation of touchscreen gloves wasn't magic. It was the integration of conductive silver or copper fibers into the fabric. These fibers act as microscopic galvanic bridges, penetrating the dielectric barrier and ferrying the charge directly from the screen to your body, effectively mimicking direct skin contact. Without this conductivity, your phone remains electromagnetically blind to your presence. Once physics completes its role in transferring the charge, the digital mind takes over. Behind every pixel you touch, a silent algorithmic battle rages to maximize the signal-to-noise ratio. The phone is surrounded by electromagnetic waves from every direction, power chargers, room lights, and even atmospheric humidity, all of which cause capacitive noise. Here, the processor intervenes with massive digital filtering to isolate only the disturbance that carries the signature of a human finger. Furthermore, modern touch systems possess an engineering intelligence called palm rejection. The algorithm analyzes the entire capacitive map. If it detects a large irregular contact area, it immediately identifies it as a palm rather than a finger, programmatically discarding the signal in milliseconds. This intelligence is what makes the experience fluid, despite the complex electrical environment surrounding us. As for the future, it seems destined to transcend the glass barrier entirely. Engineers are currently developing ultrasound touch technologies that use ultrasonic waves to detect mechanical reflections, a method unaffected by insulators or gloves. We are also seeing the emergence of hover sensing, which increases capacitive sensitivity to the point where the device can detect your finger centimeters away from the screen, eliminating the need for physical contact altogether. We are not just developing screens, we are evolving a medium for the fusion of human consciousness with digital matter, with the fewest physical barriers possible. Now you know the hidden mechanics of how your phone screen interacts with your finger, and why it ignores any glove or barrier. If you're curious to decode more secrets behind these everyday phenomena, you've come to the right place. This is the ultimate channel for that.